Hello everyone, I'm Fan Yuxin from Shanghai Tech University. I'm very glad to present our work, Post for MPC, Automated Security Policy Synthesis for Secure Multi-Party Computation. In the presentation, we start from a brief introduction to multi-party computation, or MPC for short. MPC is a powerful cryptogram. In the ideal world, Alice, Bob, and Charlie send their private data to a trusted third party. The TTP evaluates a function over their private data and returns the computation result to every party. Nothing revealed except the computation result, but there is possibly no TTP in the real world. MPC provides the ability to achieve the same effect as the TTP, so MPC have many applications in privacy computation. A main problem of MPC is the high computational and communication complexity. In the modern style, when we develop a MPC program, we use MPC frameworks. By calling the APIs, we can fastly develop a MPC program. We also need to give each variable a secret type or a public type. Secret variable is encrypted and computed by crypto protocol. Public variable is the native data in programming language and computed locally. So if a program has fewer secret variables, it will need fewer crypto computation and communication overhead. The program will be more efficient. How to declare secrets? The naive method lets all variables be secret. It's simple but inefficient. An information flow method is better. Variables related to other secrets are also secrets, but a type system doesn't reject public declared as secret, so we will need exports to minimize the secret variables. Ideally, is the information flow method the best? Our answer is no. It's conservative and it also can be automated without experts. Let's look at a simple program. Three millionaires want to know who is the richest. The program returns 1 if A is the largest, returns 2 for B, and 3 for C. The security types are assigned according to information flow. Red symbols are secret. In the right side, the table lists the leakage of some variables in different execution cases. In the case r equals 1, the Boolean value C1 is false. We can know variable max less than variable b is false, and the max is a, so the leakage of C1 is a greater than or equal to b. In the table, we can find the leakage of the result R fully contains the leakage of C2. Any party knows C2 once it knows R. We can say degrading C2 from secret to public doesn't leak more information. Our post for MPC make it formalized and automated. It's the overview of Post4MPC, receiving a program and specifying the private input data. A type system gives each variable a security type. These types construct the security policy of the program. Then the policy is degraded by a symbolic approach. The result policy are refined in the type system. Repeat until the policy is fixed. Finally, the program and its policy are implemented in any MPC framework to generate executable MPC programs. We define the leakage for MPC, both in ideal world and real world. In the ideal world, suppose a function f has inputs v hat, results in value v. The adversary has k inputs. We divide the inputs domain into many indistinguishable spaces. All the inputs producing the same results construct an indistinguishable space. Additionally, the adversary knows k of the n inputs, so he can further get a smaller space. This is the leakage. For the motivating example, it calculates the index of the max one in 3 value. Suppose the function returns 3 and adversary has inputs a with value I, so the indistinguishable space is the set of tuple A, B, C and satisfies the constraints C greater than A and C greater than B. The leakage in this case is the set of I, B, C and satisfies constraints C greater than I and C greater than B. In the real world, suppose P implements F. The leakage of P in the ideal world is equal to the leakage of F in the ideal world. There is a one-to-one mapping from program's initial states to function inputs. Let's give a policy to P. Then the public projection of the states is visible and the secret projection is invisible. If the policy is secure, the leakage under the policy should equal to the ideal world leakage. For the motivating example, also suppose this program results in 3, then ideal world leakage of P is the set of initial states. In these states, variable C's value greater than both value I and variable B's value. When P's leakage under a policy rule equal to its ideal world leakage, the policy rule is secure in the case R equals 3. With the policy, we say P is row non-interference if two executions have the same public configuration transactions and have the same results under policy rule. We provide a type system to inference a policy. In the motivating example, right-hand variables are replaced by its security levels to inference the security levels of the left-hand variables. Operations in secret branching are always secret, so variable R becomes secret even though it is assigned by a public value. The type system always produces a secure policy. It's the same as the ideal result of information flow method and automated without exports. The next step, we degrade security levels. In program P, type system gives secret level to C2, but public C2 is also secure. P contains 4 executions, 2 for R equals 3. In the case C greater than A greater equal B and C greater than B greater than A, C2 both have true value, so C2 is known even though C2 is secret, but C1 is false in one case and true in another case. C1 must be secret. Let's formalize it into executions. We say degrading X is secure if the constraint psi is valid. This constraint means T and T prime have the same value sequence about X if we result in the same value. In program P, we can write the constraints for C2 and C1. In the constraint of C2, it contains two execution path conditions, their result values, and the symbolic expression of C2. Obviously, constraint of C2 is valid, and the constraint of C1 is invalid. Now we can say a program P securely degrades variable X if for all execution pair the constraint about X is valid. It means the adversary can inference the value of X in any execution. We mainly consider analyzing secret branching variables because both branches of a secret branching are executed to protect the value of secret branching condition. This behavior usually incurs high overhead with useless computation. Furthermore, we propose a refinement to degrade other variables when some secret branching variables are degraded. In the evaluation, we firstly evaluate the performance of our POS4 MPC. In the test cases, degrading and refinement supplement each other to degrade both secret branching variables and other secret variables. The number of degradable variables are different because a program with detailed results will lead to more degradable variables. For execution time, most test cases are finished in few minutes, except meeting path explosion. We use a compositional reasoning method to alleviate path explosion, but we can't eliminate path explosion. Due to the limitation of symbolic execution, each test case has a predefined array length, so we evaluate every test case many times on different array lengths. We implement our produced security policy on two MPC frameworks. One is the obliv-C. It implements the Yale's coupled circuit protocol. In average, the overhead reduction varies from 30% to many 100%. The quicksort program is not suitable for MPC setting because it highly depends on control flow, but in our policy, secret control flows are eliminated, so it gives significant improvements. Another MPC framework is MPYC. It implements Shamir Secret Sharing Protocol. The improvement trending is similar to the obliv-C framework, but different on some concrete number. In our analysis, optimization varies by protocols. Different protocols prefer different calculations. A program with more degradable variables will reduce more overhead. In conclusion, we formalize the leakage of MPC, both in ideal world and real world. We use security policy to bridge protocol level leakage and language level leakage. We give a type system to influence security policy and a symbolic approach to degrade security levels. We achieve more efficient MPC programs without compromising privacy, and our method is orthogonal to other crypto and protocol optimization techniques. Thanks for listening. We are so sorry we can't attend Cave 2022 physically due to the COVID-19. If you have any questions, feel free to contact us.